Okay, we're going to be doing lead code 1608, special array with x elements greater than or equal x. So you are given an array called nums, which consists of non-negative integers. Nums is considered special if there exists a number x such that there are exactly x numbers in nums that are greater than or equal to x, right? And notice that x does not have to be an element in nums. What this means is, for example, this 3 and 5, right? Because this was confusing me as well. So 3 and 5 qualifies as a special array. And this is because they are numbers, two numbers greater than 2. Greater than or equal to 2. Right? But it's not 1. The answer is not 1. Right? Because yes, 3 and 5 are greater than 1, but there's no other number here that's greater than or equal to 1. So if there was maybe 1, 3, 5, then yes, but it's just 3 and 5. Yes, 3 and 5, these numbers are greater than 3, greater than or equal to 3, but there's already but no, they're not great. There's not 3 numbers. There has to be a minimum of 3 numbers, which isn't the case, right? Let's go to the next example. 0 and 0. 0 can never make an array special according to these conditions, because if 0 exists in an array, then there's already one number, which is 0, right? So 0 cannot qualify. You need a number whereby there's x or more that are greater. If that number exists, then it is a special array and you return that number. Now this is difficult because it's not an algorithm that you cannot think of the solution of how to identify just by looking, right? Okay, let's look at also this example. So you have 0, 4, 3, 0, and 4, right? So the answer here is 3 because there are 3 numbers greater than or equal to 3, right? The way the way we're going to do this, there are 2 solutions. The first one is brute force, but it uses 2 for loops, and the second one is a binary search. But the for loop solution is actually in constant time. It's in constant time because the num length is 100, but also the highest possible value, because our nums is between the values are between 0 and 1000 inclusive. So the highest possible value is x is equal to 1000. And if you're trying to see if x is 1000, then it can't be the solution because the length of the array is only 100, right? So you need to have at least 1000 numbers greater than or equal to 1000. So 1000 itself cannot be. But in order to exhaustively search, you search from 0 to 1000 as are possible values of x. And for each of these, we check by looking through nums and seeing how many times it occurs. A number greater than or equal to x occurs. And if that number of occurrences is equal to x, then we have found a special character and we return that character. Otherwise, we return -1. Right? Here they say return x if the array is special, otherwise return -1. Another thing they say, it can be proven that if nums is special, then the value for x is unique. This means that if that number exists in the array, then it will be the only one, right? It will be the only one in the array. So as you can see here, right, 3 exists. I mean, there are 3 numbers greater than or equal to 3. So 3 is the answer, but it exists only once, so it's unique. But this isn't much of something to think about. So let's start with the brute force solution, which we've ascertained is in constant time, because it's so we'll say brute force solution, which will be our population. I'll call it our population size for possible values of x is 0 less than or equal to x less than or equal to 1000, right? So we iterate over the possible values of x and check for the number of occurrences of x greater than of num greater than or equal to x in the nums array. If this count is equal to x, then we have a special array and return x or count. So let's do that. We need a counter, so we do that. We need a counter. So counter is equal to 0. Then we iterate through possible values of x, which will be for x in range 1001, right? Because we want to go from 0 to 1000. Remember, Python stops at the second last position here. So then actually the counter needs to be for each. So we need a counter for each, right? So we iterate through possible values. We need a counter for number of greater than or equal to x in nums, right? So we do it here. We're like for num in nums, right? If num is greater than or equal to x, right? If num is greater than or equal to x, then we increment our counter. So counter plus equals 1. Then if our counter is equal to x, we have a special array and we return x or counter. So if counter is equal to x, then we return x. If we reach here, then we looped through all possible values of x and found none. We found no instances of numbers in nums array which are larger or equal to x and occur x times, right? So we simply return -1. This takes constant time because it's 1000. And this here is actually length 100. So this is 1,000 times 100, which is constant time. Even if this was like n, if this was like if n was to infinity, then this would have been 1,000 times n, so it would have been an O of n solution. Voila, it works. So we're not going to use this solution. We're going to use, because an interviewer may decide to say that, no, this is not optimal. I don't care if it's constant. I consider this n, right? So one, that shows you that the interviewer doesn't know what they're talking about, but you don't argue with the interviewer. And what you do is you simply move forward with a more optimal solution. So the more optimal solution is we're going to do the counter part, this part, but instead of looping through, we can binary search. And the reason we can binary search is that this is in ascending order, right? So since that is in ascending order, let me draw it up here. So we can do it in ascending order, right? From 0 to 1,000 inclusive, we check, we find a mid, and then we check if we check through the nums array. Then if the number of occurrences is equal to mid, we return mid. Otherwise, if mid is less than the number of occurrences, then we push out, we want to get rid of all the values, including mid, right? Otherwise, if it's greater than, we want to get rid of all the values as well on the right hand side. So let's do the binary search solution. So the binary search solution is I is equal to 0, j is equal to 1,000, right? So while I is less than or equal to j, we get our mid, which will be mid is equal to I plus j divided by 2, but as you know, some people factorize it as I plus in brackets j minus 1 divided by 2, right? And now we check in nums, right? So we have our counter is equal to 0. Then for num in nums, if num is greater than or equal to mid, right? We could have called mid x, right? Or possible value of x. So we get our mid, which is a possible value of x, right? Then counter, here counter plus equals 1. So now we check using binary search. So if counter is equal to mid, then we simply return mid or counter. If mid is less than counter, then we want to get rid of all possible values of x less than or equal to mid, right? So I is equal to mid plus 1. Else, this means mid is greater than counter. So we want to get rid of all possible values of x that are greater than or equal to mid. So j will equal to mid minus 1. So once we get out of this loop and we still haven't found it, we simply return negative 1. So let's run this and see. Voila, it works. And this is log of n, log of size of the possible, so log of 1,000 times length of n, right? But this is essentially constant time. But another thing that we can do is, this works for length of nums as well. This will also work. Oh, what the hell happened? I didn't mean to pop that up. This works for length of nums as well. Hold on a second. Yeah. This works for length of nums. Hold on a second. Yeah. What was it last time? Okay. Another option maybe if you started from 1 to length of -1. No, okay, from 0 to length of nums should work. And the reason this works is because our possible values of x when using the binary search, they are not going to exceed the length of nums, right? Because the size of the array actually constrains how many possible values you could have, right? So when we're doing the brute force, we're just exhaustively searching through whatever was possible. But here, we know that it will never exceed the size of nums.